welcome to lecture 5 of the topic operating system. In this lecture, we will be continuing our discussion on process. We already have seen what is a process, what constitutes a process, and how a process gets loaded onto the memory and how the OS maintains two views of that in order to work with the process. In this lecture, we will be talking about what are the operations that we can do on a process and how OS helps the user to perform those operations. Okay. So OS provides some interfaces for process management. These interfaces are nothing but the system calls. Okay. So if a process wants to perform or the user wants to perform some process management task, it has to make use of those system calls provided by the corresponding operating system. So while discussing about the different operations, we will be restricting ourselves to the Linux-based system calls. So the operations that we will be discussing about in this lecture will be, we'll see first how to view the status of a process, then we'll move on to discussion about how to create processes, how to terminate a process, and how to overwrite a process by a different process image. So let us first begin with discussion about system calls for viewing the status of a process. Now we know that a process is, whenever a process gets created, there is an address space which is allocated to it. If you remember that some portion of the process, and this is the memory image of a process, then some portion of this process is executed in the user space, and some of that is in the kernel space. Now the one that is actually in the kernel space is mapped to the kernel code in the physical memory. Right? So this is the physical memory, this is the kernel. So they are actually mapped to the OS to this portion, which automatically means that anything which falls in this kernel space, the process cannot execute that. It has to request the kernel to provide that. Okay, and how does a user process request the kernel? Through system calls. So within this process address space, the information about the status of the process is maintained by the kernel. As a result, the process cannot see its own status. It has to request the kernel to provide the status of it. Say, if the process wants to view the process identifier of this particular process, okay, that is maintained in the status of the process. As a result, the process has to request the kernel to provide the process identifier, and Linux provides certain system calls for that purpose. Get PID is a system call which is used to get the process identifier of a particular process. We'll see the working of this by using a code. Now, in addition to that, if you would like to view the process identifier of the parent process of this process, okay, so the system call to be used is get PPID, get parent PID. So that gives you the PID of the parent of this particular process. Okay. In addition to that, the Linux allows certain commands for viewing different processes. Say, for example, there's a command called PS, process status, that allows you to view the status of all the running processes currently, all the processes that are currently running on your system. Let's look at the second operation, that is how to create process. Processes are direct or indirect descendant of other process. That means, in order to create a process, you need help of some other process. So that means a process P will give rise to another process. Okay, and how? So a process P, it utilizes a system call called fork, and on using this system call, P clones itself. That is, it creates a copy of itself. So a fork system call performs a cloning operation. The process which was executing, the moment it makes a fork system call, it creates a clone of itself. Though I say that it's a clone, this process is a new process which is created. So let's look at this diagram. So the process P has made a fork system call, creates another copy of itself, which is P. So if this P process P, which had made the fork system call, had, let us say, a process ID 2048, on making this fork, it creates one more process. So this is the process that actually had made the fork system call. This is the 2048, and this creates one more process with a new process ID 2049. Okay, which means that this is a new process that is created. And if it is a new process, it automatically means that this process will also have its memory image. Right? So 2048, which was the process that eventually had made that fork system call, has its own memory image. 2049 has its own memory image. But the contents of both of them are same, because it's nothing but the clone of the parent process. Okay, of rather the process that created that. So the newly created process is called the child process, and the one that created that is called the parent process. So you see, processes are created from other processes. One process makes a fork system call, eventually leading to a clone of it being created, and the second process that gets, or the new process that gets created, is called the child of the parent. Right? The child and the parent, both, though being same code and data, however, they are two independent processes. They have their own memory image, right? Okay, so this is how processes get created. So all processes that you find in your system have been created from some other process. So you may wonder, who was the first process that led to the creation of all other processes? And that is the process that starts this whole procedure of creation of process is called the init process. So this is the process that is started the moment you turn on your system. So this process often has a PID equal to 1, and that eventually creates other processes. They then create other processes, and this way the process creation starts. We'll talk about how processes are created from other processes and they are overridden by new process images when I'll come to discussion about the execute or EC system call. So for the time being, let's talk about how a fork works. Okay. So to understand about the fork system call, let's look at this code. So here's a code, and let's say this piece of code, which is called test_fork.c, has been compiled, and that has resulted in a process called a.out. So here we have this process called a.out, and let us say this a.out process has a process ID 2048, and what do you have in this process? Okay, so this code and data and the rest. So let's say this is the other portions, the kernel portion, the stack, the heap. I'm not interested in that. Let me just write down the code and the data portion. Okay, so I'm just showing the code and the data portion of this process a.out. What do you have here? We have a printf statement, we have a for, and we have a printf statement. Now let's see what happens when this code gets executed. Okay, so the first line that gets executed is this printf. So automatically the string that is passed on to as the argument to this is printed at the output. So let me see what the output is. So you find this string before for gets printed. Right. Now, following that is the fork system call, which means that this process now creates one more process. Okay, one more process. So let us say this is 2048, this is A dot out, and this is also A dot out. But this is 2049. It's an independent process. But it's the clone of the parent. So this is the parent and this is the child. So what do you have in this parent? You have all the other segments of the memory image. And let's concentrate only on the code portion. So what you have is the printf statement, then we have the for statement, and then we have a printf statement again. And then we have, in this case as well, we have the printf statement, we have the for, and we have the print. Okay? Because the child is the clone, so you'll have the same code and data present in both of them, but they are two different processes, they have two different memory images. Right. Now, because now we have two processes in our system, obviously we would like these two processes to work in a time sharing way. That is, sometimes this will be working, will be scheduled or will be allowed to execute with the CPU, sometimes this process will be executed. Okay? So let us assume that the parent is the first one to get executed. So something to keep in mind here. Number one, now that there are two processes, both of them will get a chance to get executed on the CPU. So that is, their code, this code will be executed sometimes, this code will be executed sometimes. You may wonder who will execute first, who decides. Okay, that's completely decided by the scheduler. We don't have any role in here. Whether the child will be, that is process number 2049 will get executed or 2048, when, how, the scheduler will decide. How that is being decided, we'll talk about that in the next lecture when I discuss about process scheduling. For the time being, let us assume that this can also get executed, this can also get executed. So that's the first point. The second point to note is that when both of them start execution, that is, when a child has been created and now parent and child both can execute, the execution will start in both of them after the line from the line following the for. Okay, so even though 2049 has replicated all the code of 2048, however, the execution of 2049 and 2048 automatically has done this, so or it should start execution from here. But even for 2049, which was just newly created, will now start its execution for the line after for. That means this line. So if you look at the execution after the for system call, the execution of both of them will eventually start from this line. So let us assume that the parent executes first. So the parent executes this printf statement, which means this after for. Okay. And then it terminates because it's over. Now 2049, or the child gets a chance to get executed. It executes this line, which is this printf, because we said that the execution of the child will start from the instruction following the for. That is only this, and it also prints after for. So this is what you find at the output of this statement. Okay, so let me quickly summarize. In order to create a process, Linux provides a system call called fork, and fork is a mechanism by which a process creates a clone of itself. That is, it creates one more copy of the process. However, the process that gets created, which is called the child, is a new process, so automatically it gets a new process ID and a completely new address space, that is, it has its own memory image. However, the content of the memory image of both parent and child are identical. So you find that the code present in both of them are identical. But since these two processes are two different processes, obviously now they will be working in a time sharing way. Because sometimes the parent code will execute, sometimes the child code will execute. Who executes first? That's decided by the scheduler. but both of them will get a chance to get executed. Okay, but the execution will start in after if there's a fork and a child has been created, the execution of both parent and child will start from instructions following the fork system. So that is what we saw, and eventually this is what we find as the output. Now, this is okay, but there's a problem because we just saw that whenever this code gets executed, okay, and a child has been created, we don't know which is working, whether it is the parent or the child. Is there some way by which we can decide whether we are working in the parent process or we are in the child process? So let's see that. And the easiest way to do is, if I have an idea of whether I am in a parent or in the child, okay, and for that we make use of this fork system call. Interestingly, fork, because it's a system call, it returns some value, right? What does it return? It returns 0 to the child, and it returns the child process ID to the parent. So that's very interesting. The fork system call, it returns a value both to the parent and to the child. To the parent, it returns the process ID of the child, which is a positive integer, because process IDs are positive integers. And to the child, it returns 0, because I don't have that. To the child, what will it return? It just informs that, okay, you are the child. So we can make use of this return value of fork to decide whether I am working in the parent process or I am working in the child process. It's a very interesting thing. Let's see how. So let's keep this before fork line, and let's make some modifications here. The first modification we'll do it. Let's introduce, say, an integer called return value, RV, and what we'll do is, now previously we had fork a process, but we did not know, or we did not keep the return value of that. Now let us store the return value of fork, and let us try to decide based on this return value. What do we do? So what we'll do is, we'll check whether RV is equal to 0. So if RV is equal to 0, that means if the return value is 0, now we will be printing the string that I am the child, and say my PID is, okay, we have this get PID call to be used here, and if I am not, then I would like to print that I am the parent and my PID is, say, I get that from the PID system. So let's try to see what happens if we execute this code. Okay. Right. So let us assume that this is also some process called a.out, and here you have this a.out. Okay. So this a.out has a process ID, let's say 2048, and what do we have in this 2048? We are not considering the other factors, let's only concentrate on the code and the data portion. So this 2048 has a printf statement, the first printf. Then we'll have the fork, okay, and then we'll have this if block. Now the if block, so I'm writing it as this if block, and within this if block, then we'll have a printf statement within this if block, and then I have else block, and sorry. So this is the else block. We'll also have a printf statement in this else block. So this is what my process is supposed to do. Okay. Right. So the first printf statement will eventually lead to. Okay. So the printf statement will lead to this line in printer. So let me write down the output here. Okay. So it will be before for. So the process will execute this line first. Then we'll have a fork. Right? So we'll have a fork, which means that 2048. So 2048 will create another process. And let us assume that this is a new process that gets created. Its process identifier is 2049. And because it's the clone of the parent process, the child is the clone of the parent process, all the code and data that we have in the parent process will also be copied into the memory image of the child process. So you'll have the same printf, and we'll have the for, okay, we'll have the if block, we'll have a printf here, and we'll have the else block, and we'll have a printf here. Okay. So let me just write down this rb equal to 0, and so that we'll have the printf, we'll have the for, then we'll have this rb equal to 0, we'll have this printf, then we have this else block, and we also have this printf. Okay. Now interestingly, so this is rb, this is rb. Okay. So when the process creates this child, when the process has created this child process, we just saw that when two processes have been created, now they will work in a time sharing way. So let us assume that the parent process has been allowed to execute first. It can be other way around. I'll show you the other way around as well. So let's assume that the parent process has been allowed to execute first. So if the parent process will execute, then it starts from the instruction following the fork system call. That is, it starts executing from this line. And the same is true for the child as well. So let us say if we have the parent, and the parent executes this instruction, we are checking an if condition, and we are checking the return value of the fork. We just saw that fork returns PID of the child to the parent. So definitely it's not equal to 0, which means it falls into the else block. Because the return value of the fork for the parent process is not equal to 0, so this condition is false, which means you fall into the else block and you execute the instruction within the else block, which is this printf statement. And what you print here is I am parent and my PID is, so what you print is I am parent and my PID is 2048. Okay. Now, once the parent is done, you switch to the child process. Now the child process starts executing, and as discussed earlier, the child process also starts execution from the line following the fork, which means this line. Now the child will also test this condition, but for the child the return value is 0 because we studied that fork returns PID 0 to the child. As a result, this condition will be true for the child, and if this condition is true for the child process, this printf statement will be executed, and which means that this line, which is I am child and my PID is, so what we'll have as the next line will be, so I'm writing it here, so we will print I am child and my PID is 2049. So we have these three lines being okay. So let's summarize. So in this code, what we did is we kept track of the return value of the form. We stored it in a variable called RV. We checked that and we decided whether we want this, whether we would like to execute something while in the parent or we would like something to execute while in the child. So we applied an if condition and we found that we want this line to execute if you happen to execute the parent process, and I would like this line to get executed if I'm in the child process. So how did I do that? Okay, so when the parent process started execution, it executed or went through execution of this line, that is it printed this before fork, and then it forked a child process. So a child process got forked and the return value was stored in RV. In parent, it was the child process that was the child PID that was stored, and for the child it was 0. So now this is what the situation is once the child has been forked. Now we look at the line following the fork, because the execution now starts in both the processes from the line following the fork. So the first line that gets executed is in either case. If it is the parent, then this line, the if condition is checked, and this state the condition becomes false because for the parent the return value is not equal to 0. So it falls into this else block and it prints this line. That is, I'm the parent and my PID is this. Okay, once it is done, now it's the turn of the child to execute. For the child, again, the execution starts from the line after fork, which is testing this if condition. In this case, the if condition becomes true, so that executes the line within this if block, which is this print statement, which says I am the child and my PID is 2049. That's interesting. This is how we can make use of the return value to print whatever we want and to decide whether we are executing the parent process or the child process. Now you can add the RV value to this. So if you add one more line to this printf, to this if block, say we have a printf where you would like to print RV equal to, so you will find that in case of child this value will be 0, and if you would like to do the same for say for the parent, if you try to do the same, you will find that the parent prints the child ID, which is 2049. So the RV value for this parent is 2049, whereas the RV value for the child is 0. So this is how you can make use of the return value to print something in the parent or the child. Okay. Now we know how the parent and the child can be made use of. Now, can we do something where we can force ordering of the parent or the child? So that means whether we may cause some process to wait until the other process finishes. Let's say if you have a parent and if you have a parent-child process being created, and you would like the parent to wait for some time before the child. Okay, so let's look at such code. So maybe okay. So say we have something as okay. So let's take two variables called PID and status, and say we would fork store it in PID. Now we check whether PID is greater than 0. If it is greater than 0, we know that it's the parent, and now what we will do is we will use a system called wait. Okay. And then I will print I am the parent. Okay. So say this is what we have. Now else, that means if this is not true, you are the child and you would simply like to print I am the child. So this is what you would like to do, and I will use. So let's see what happens here. So this is a process. Let's say this process is also something like a.out. With process ID 2048, and this process starts execution. So 2048 starts execution. What do we have here? We have something called, okay, so I'll do it this way. We have a for, then we have an if condition check, and then we have a printf, and then we have an else block. Okay. And within that okay, so if this condition check, sorry, we have a system call called wait, then we have a printf statement, and here again we have printf, and we have an exec. So this is your a.out or 2048. So as we have seen in the other two programs, the execution starts and we hit upon the system called fork. So the process creates a child process. So now two processes get created. One is process 2048 and we have a process 2049, and both of them get the same code. Okay. Now we have the same code here. Now interestingly, I'll just show this part. The wait, the printf, and then we'll have the else. We have the printf. Okay, so after the child process gets created, we know that both of them, they start executing in a time shared way, and this is the point of execution. So this is from where both the processes start executing. Sometimes the child process gets a chance, sometimes the parent process gets a chance. But interestingly, what we have done is by applying this, so the if condition will be checked. Let's say we are the parent, the if condition gets checked, and if condition says that if PID is greater than or equal to 0. So if you are in process number 2048, automatically it means that this condition will be true, and if this condition is true, you will enter this if block. Okay. So if you are in the parent process, this condition will be true. If you start executing the child process, this condition will be false. It depends on the scheduler, which of the two processes the scheduler allows. So let's assume that the scheduler has allowed the parent process. So this condition will be true. So if you fall into this if block and you execute this wait statement. So the moment you execute this wait statement, the parent is put to sleep. Okay. So that means it does not proceed execution. The moment it is forced to wait, the scheduler picks up the child process and allows it to get executed. So the child process starts execution from this instruction. It sees that this if condition is false, so it falls into this else block and starts executing this printf. So what it prints is this line, that is, it prints I am the child. Okay, and then it comes out. And once it comes out, that is, it completes its execution, it sends this message to the parent process that I have finished my execution, and that is done through this exit system call. So this exit system call is kind of an information to the process, the parent process, that I have completed my execution. So the moment the child terminates and the parent is aware of that the child has terminated, it resumes its execution for the next line following the wait, which is this printf statement, and then it prints I am the parent. So what we did by using this wait and exit is we forced the parent to wait for the termination of the child. So both the processes, they were both the processes started execution. Had not we used this kind of wait, we would not have, the scheduler would have decided who will be working. But by introducing a system call called wait, we ensured that the parent would wait until the child completes its execution. So this is how, by a wait exit pair, we can make sure one of the processes to be executed while the other keeps waiting. Now let's look at a very interesting situation that happens while you fork two processes, and in this situation we'll find that one process, it terminates before the other. Let's look at this code. Okay. So here we have a process that forks another process, and the moment it forks, let's say the process called 2048 is the parent that forks another process and gives rise to a process called 2049. Now, when we have a parent and a child, we just saw that they will both be working in a time sharing where any one of them can work. Okay. Depending on the return value, we will decide whether we are executing the parent process or the child process. So let's say if you are in the child process, then the child will start executing from this line and will print this statement. So the child will print this statement, and then it is put to sleep by using this system called sleep. So the child is put to sleep. The moment the child is put to sleep, obviously the control transfers to the parent and the parent starts executing. So the parent executes and the parent starts execution. It starts execution from this if block. For the parent, this condition will be false. So obviously it falls into the else block, and when it falls into this else block, it will print this statement, which is this. And the parent terminates. Okay, so the parent terminates. Now, when the child resumes, that is, it wakes up, the problem is that the child, which previously knew that it had a parent 2048, now this parent has terminated. So there is no parent. And because there is no parent, the child now is called an orphan child. Okay. So this is the situation that can arise when a parent terminates before the child. Okay. So an orphan child is its parent terminated before the child. But no process can exist without its parent. So in that case, the operating system comes to the rescue. And what it does is, it assigns the init process. It assigns the init as the parent process to this process, the child process 204. So in case of situations where a child becomes orphan, the operating system assigns the init process as its parent. So now if you look at the PID of this child, you'll find that, so let's introduce one more line after this. Okay, the same printf statement, if you introduce after this, you'll find that the parent in this case is the init. Okay, so the next operation that we are going to talk about is process termination. Okay, So what happens when a process, and how does a process terminate? And there can be two ways in which a process can terminate. One is a voluntary termination, that you reach to the end of the execution. We have seen already the three codes previously, where we use something called the exit system call, right? So that means you inform that the execution of this particular process has completed, and you return the status of this. So the status of this particular process is returned through the exit system call. So what happens is, if there's a child which had exited, so the information that the child has completed its termination is sent to the parent through this exit system call. Okay, and the parent which was waiting for that particular child information is the parent uses the wait system call to read the status of that particular child. Okay, so once a process has terminated, all the resources that have been associated to that particular process is taken back by the operating system. So that is the usual procedure. That you complete the execution, you inform the parent that okay, I have completed, and the parent knows that because it has used the wait system call, and the OS automatically takes back all the resources. That is all the space that has been given to the process. Okay. But there can be an untoward situation as well, where the process was forced to terminate. So in that case, you use the system call called kill, right? And you pass on the argument which is the PID of the process that you wish to kill. So kill is a system call that kills a particular process. The process that needs to be killed, the PID of that has to be passed as a parameter to the kill system call. Okay. So you may have often seen that a number of times your processes hang up, and then you have to click on the force quit or the close button. So that's nothing but you are killing a process. And for all those who work with Linux system calls, in case you suppose a process is taking too much of resources and you want that process to be killed, you have to open up the process manager, that is, you go to your ps command, and then you find out which of the processes is occupying your maximum resources, find out the PID of that, and then you type in the kill command followed by, let's say, 2048, and that kills your process. So this is how this works. Okay, and the moment you type in this kill, what happens is a signal is sent by a process. In this case, you saw that I wrote this command called kill, so it's nothing but a signal to that particular process that you need to be terminated. So the OS forcibly terminates that process and takes back all the resources given to it. So that is how a process termination happens. Now there's an interesting thing that happens in case a process terminates, but that information is not read by the parent. So let's say there's a process, a parent process that has forked and resulted in a child process. The child process has exited, but there is no wait here. That means the parent did not read the exit information of the child. So if that happens, then even if the child has completed its execution, remember that the process image, the memory image of a process, contains some information which is maintained by the kernel. What is that? The status. And what do you have in this status? The kernel maintains a data structure called process control block as the status of that particular process, the PCB. Okay. So 2049 had exited, but 2048 did not read the status, the exit status of 2049. Why? Because it did not use the wait system call. So it did not read the status, and somehow the child terminated, which means the child got killed, but all the resources were taken back from 2049, but the information about 2049, that is its PCB, still exists in the kernel. Okay. And this status of the child process 2049 in this case, let's say, is called a zombie. That means it's a defunct process which has terminated, but its information, that its PCB, is still remaining in the system. So that is the status of a process, and we call that status as that particular process as a zombie process. The process terminates because it becomes defunct, but the PCB in the OS still exists. Why did it happen? Because the parent did not read the exit status of the child. Okay, so what is the harm in having this kind of thing? It just occupies a lot of space. So you see, PCB is a data structure maintained by the kernel. So if you have such kind of processes which have completed their execution, but their PCBs are still remaining, which means that you are unnecessarily occupying some space. Okay, so if the number of such zombie processes keep on increasing, that will eventually, disturb the operation of your system. So what to do? So it's the responsibility of the process, the parent process, to read the child. And how does it read the child? Okay, so it puts this wait system call to read the status. And when it reads the status, it understands that, oh, this process has terminated, so I should inform the OS that please remove the PCB. And then the zombie process is declared killed. So this is how we perform the process termination. So please refer to the course website where we have given enough course regarding the fork system call, the wait, the exit, the zombie process and the orphan process. Please download them and execute them in order to understand how these work. We'll also be providing tutorial videos on the course that I have discussed in this lecture. Okay, so now let's see one more operation, and we call that process execution. What do I mean by this? Now we argued that, okay, processes, in order to create processes, we need to use the fork system call, and then you'll be able to create a process from another process, right? But now, let's say I would like to have a new process image altogether, because we saw that what we do by fork is we replicate the process, right? So let's say we now want a new process image. So the idea is we'll be first having a process P, or maybe let's say a process called P1. The process P1 forks, so it creates the parent process. It's the parent process, it creates another process called the child. And now this child will be overwritten by a new memory image. So that is the whole idea. So that this gets overwritten by a new image, a new program altogether. So you have a new process with a new set of code and data. Because we saw that, say this P is 2048, okay, a fork eventually creates, so what does it create? It creates a new process, which is the child process, but the code and data, okay, so the code and data, that's the same for both of them. So that's identical, right? The code and data are identical. Now if you somehow happen to override this code and data by a new program, so you have a new piece of code and data which will be executing, alternating between this code and this process and this process. So that is the whole idea. So you first fork, create a clone of the previous process, and then you override that new process by a new program. So there we have a new code and data which has replaced the code and data segment of this child process. So let's see this by code to understand this part. So we have the same thing. Let's say we have variable called RV, then we fork and we store it in RV, and if RV is greater than 0, okay, we do the put a wait, and we wait for the child to terminate. If not, that is if you are the child process, so what we'll do is we'll make use of a system called exec, that is execute. Okay. And what this execute does is it simply takes a parameter which is the new program. Let's say the program is called ls. It takes this new program and it overrides okay. So this is what happens, which means that if you are, let's say this is the process called a.out, so we have this a.out, okay, which is, let's say, 2048. Now, the moment you execute this fork system call in this process, it creates a clone of itself. So we have 2048 and we have 2049. So till this fork is executed, everything is the same. So that means we have RV equal to fork, then we have this if block, then we have this wait, and we have this else block. The same thing, RV equal to fork, we have this if block here, wait, and this else block. But interestingly, okay, now let's see if we are in the parent process. So after the fork, maybe the parent starts executing first and it executes this if block. So if it executes this if block, it hits this wait call and it waits for the child process to terminate. So the control shifts to the child process, and what the child does is it checks this RV greater than 0. So it starts its execution from here. It finds that this is not true, so automatically it falls into the S. And in the else block, we have used something called the exec, which is an execute system call. And what it executes? A new process altogether, a new program. So it takes this new program called ls. So ls in this case is the name of the program, which has been compiled and it is there. So this process is already, this executable of this particular program is already available somewhere. So what this execlp does is, it simply takes that image and now it overrides this by the ls program. Okay, because it overrides this with the ls program, now the child executes this ls code, and if it executes this ls code, whatever you would like to execute due to ls gets displayed. And what do we have is the list of files and folders of your current working directory. Then it exits. This information is known to the parent. The parent then wakes up and completes its execution. So you see, what happens is this process called a.out, fork and create another process, okay, a.out, and then it was overwritten by a process called ls. Now you have two processes, a.out and ls. And this is how you create processes from other processes, by using this fork and this execlp. So the rule is, you take a process, allow it to fork another process, and replace the newly created process by a completely new memory image of a different program. And then you have two programs which are running in a time sharing way. And that is exactly what and how your system creates different process. So we have a first process called init, which starts the moment you turn on your system, which has a PID, let's say, equal to 1. Now this eventually gives rise to another process. So it forks, it creates, say, a child process, which is its clone, and then it is overridden by another completely new process by using this exec, and say we have something as a new process called modem, okay, which which starts the modem manager, and in this way you have different other processes which get created. So what we have is, let me show you. Okay, so this is the way that we can create different processes, and okay, so we have, say, init again can lead to byte daemon. Daemons are processes that run in the background, they always keep on running. This maybe this gives rise to, say, a new process called DH client. So you see how one process gives rise to other, and gradually you have a lot of processes which get created, and this is what we call the process tree. So this is the way in which you create a process tree in Linux. So the idea is there is one process that starts the moment you turn on your system. That forks creates a child process. The child process is overridden by a completely new program. Now you have two different programs which are running. Then both of them may again fork, create again a new clone of itself overridden by a new program, and this way you have gradually a lot of programs that get created. So this is the idea of program execution. And now let me complete this lecture by a concept called copy on write. This COW. That's a very interesting concept. We saw that when we were discussing about fork, we said that a fork creates a child process, right? So a process P, the moment it uses a fork, it creates a child process. Okay, and now we have two processes, but we argue that both the parent and the child, they are individual processes. So as a result, they have two different address spaces. So this is, let's say, the address space of the parent, and this is the address space of the child. Because they are two independent processes, so they definitely have two different address space. So when these address spaces, and by the way, these address spaces are virtual address spaces. So each one of them can be considered as consisting of a number of pages. So let's say if there are 4 pages which make up the address space of parent, obviously the same address space, because both are of the same, they're clones, so the range of addresses for this will be same as this. The number of pages created in parent will be same as number of pages created in child. And now we started that if this is the address space of parent, now the mapping to this, say this is the 4 pages of the parent, say. So this is parent process P1, this is parent process page 2, this is parent process page 3, and this is parent process page 4. So what this page table of parent process will hold is mapping of these 4 pages. Right? Okay. Similarly, if you talk about the address space of the child, there will also be a page table which will contain same mappings, and this will, let's say, the page table of child 1, the page table of the page, third page of child 2, this is say the fourth page of child. So now this will contain links to this. This is this, this is this, this is this. Okay, this is what you see. But the problem is that there is no reason why we should have an identical copy of these pages for both parent and child. Okay, why? Because the content of both parent and child are identical. So there is no reason why in the physical memory we should have a copy of both parent and child. Rather, what we can do is, or what this is the ploy that the current operating systems they do, instead of having two pages, they share these pages among both the parent and the child. So the moment a fork happens, right, if you have a fork, the first thing that is done is, now these pages are created, let's say page number 1, page number 2, page number 3 and page number 4. So all that you do is, instead of having separate pages for both parent and child, the same 4 pages are shared among both the parent as well as the child. So that means this is how the mapping is done in the page table. Now similarly, the child will also have the same mapping to the same page, okay, because it's identical. Okay, and these pages are made read-only. So that is, when the parent process or the child process reads them by looking up to their respective page tables, okay, now these pages can only be read. You cannot modify them. So there is no chance that these pages will be tampered or they will be updated. So you can simply read them. Now the problem is, if your child happens to make some changes in some variable which the parent has not made change. Say for example, the parent uses some variable which is I equal to I plus 1, whereas the child would like that to change to I equal to I plus 2. So there's a variable that has different value in a parent and has a different value in the child. In that case, there will be a problem. So what we'll do then is, we'll look at the page corresponding to this change in the variable and we'll identify that page. Say for example, this is the page where this updation of I happens, and this is the page of the child where this updation happens. So accordingly, those pages will be identified. Let's say this is the page. So this page now, the third page, okay. So what we'll do is, so the first 2 pages, because they are identical, okay, because they are identical, so this is page number 1 and page number 2, so these 2 pages will still have the same mapping for both the parent and the child. Now for these 2 pages, you have to have a separate copy of them. So this third page will have the parent and will have a child copy, and this fourth page will have a parent and a child copy. So that this will now be, so this will now be pointing to this, and this will be pointing to this, this will be pointing to this, this will be pointing to this. So these are the pages now which are not read-only, and they will have the separate copy for both parent and child. So that means when you would like a certain page to be different for a particular parent or a child, only those pages, they need to be made writable, and you can make 2 separate copies of that in the physical memory for these pages only. And that is the concept of copy on write. So you copy those pages first and then you write. So that is about the process operations, and I've already stated earlier that the codes are available. Please download that from the course website, execute them, and see how these concepts can be implemented. So in the next class, we'll be discussing about the scheduling techniques for processes.